In this section, we would try to develop a relationship with science and physics. So it is not about getting marks, right? I mean, science and physics, the study of science and physics is not only about getting marks. I mean, that's one thing. Of course, if you're good in science or physics or good in maths or any other subject, you would score good marks. That's a given. But that is not the ultimate objective of why we are studying all these subjects. It is actually to develop some kind of love, some kind of affection for this, some kind of relationship with these subjects. And then in turn, if we like these subjects, then we will automatically get good marks without much struggle. And that is the intent. So this chapter, you might think that it is, this section you might think is not so useful. Why are we even going into this? Why should we should just leave this? But that is not how we are going to do these things. I mean, we are going to learn the subject of physics by we'll learn to love the subject of physics. That's how we will understand everything, yeah, through our lectures. So before we delve into the more intricate aspects of physics, let's just understand what is science. What does science, when we say science, what is the objective? Why are we even studying science? What's the purpose? See, the first thing is that there are various natural phenomena which occur all around us. They happen, right? I mean, we don't have to do anything. We are simply an observer, right? For example, the sun rises every morning. We don't have to do anything. We just wake up in the morning and it's there. Now it's up to us to make sense of it. Why does it rise? Where does it go? I mean, night falls, where does it go? It's for us to make sense of that reality. The reality already exists. There are some laws which govern the rising of sun. It's up to us to understand what those laws are. And this is the ultimate purpose of science. To really understand those laws which govern the things around us, which govern this universe, each and everything in this universe. And the science is so powerful. Physics is so powerful that if we understand those laws, if we completely understand how each and every atom, each and every quark, each and every boson, how those particles, each and every one of those is interacting, how it is moving, if we are able to predict it, if we are able to understand it, then we can understand the future completely. Then I can tell you what is going to happen the next second, and the very next second, the next hour and the very next day, right? I have ultimate prediction power, and that's the power of science. See, with this power of science, we already are predicting some things. That is something that we are doing right now. For example, we can predict when summer would come, when winter would come. We can also predict when storms would come. Who gives that prediction power? It is science. It's the power of science. It's the power of physics. And that's why we have to study this subject, because it is the ultimate of ultimate subjects. It is just giving, understanding science and physics would give you ultimate power. It will just help you understand how things work around you. Once we understand the natural phenomena, all of those natural phenomena, then it gives us another power. What does it, what power does it give? So for example, if I understood how the birds fly, I really understood the method, then I can use the same technique to develop an airplane. Once I understood how the birds fly, then it gives me the power to develop an airplane. So that's how this process of science, that's how powerful this process of science is. Everything, each and everything that we see around us, the remote control, mobile phones, televisions, the screen on which we are viewing this lecture, everything, each and everything that we see around us, which is man-made, has actually in some way or the other been inspired by the natural laws that we have, or our predecessors, those scientists, the great scientists, have actually observed around us. Right? So once we observe nature, we understand how nature works. Those same laws we can then apply to create new things which facilitate our life, which help us lead our life easier. And that is what this entire slide is telling you in so many words. Okay, this is the scientific method. Now, why we are looking at this method is it helps us understand why scientists struggle so much, right? I mean, in the other class that I took, we understood the model of atom. Now, as you would have understood, you would have read through all of these classes, there was not one model of atom, there was not two models of atoms, there were several models of atom. Now, there is one small thing, atom, which is there everywhere, right? I mean, you can't imagine anything without an atom. And yet, the scientists, the physicists, they struggle so much understanding what that atom looks like. And why is that the case? Why is it that the case? Right? See, one of the things that the physics and the scientific method actually gives us, it gives us the power to reach the ultimate truths, right? So I can make a prediction, right? That is what this lady over here is doing. She's asking a question: why does this work? Why does the sun actually rise? Then she's trying to form a hypothesis. So the hypothesis is just a statement saying that this is why I think something is happening. So for example, I might really say that sun is rising because earth is at the center of the universe and the sun revolves around the earth, and therefore the that's not actually the case. Okay, I'm just deliberately going wrong here. Okay, and that is why we observe the sun to be rising, because half of the time it is revolving around the earth. So half of the time it is in front of us, half of the time it is towards the back. So that's why that is what the first theory was, the earth centric or the geocentric theory of the solar system was, right? It said that the earth was at the center of the universe. Of course, now we know that that is not the case, right? But let's go along with that idea. So she actually formed an hypothesis. She made a prediction that, okay, this is what would happen if this hypothesis was true. So for example, I would make a prediction that if my geocentric theory, where earth is at the center and the sun actually revolves around the earth, if this was true, then I would make a prediction that such and such thing would happen, that the sun would rise every morning at this time and the sun would set every morning at this time, and this is how things would work. Now I would test this prediction. Okay, and then finally, based on my testing, I would draw conclusions and then present my finding to the rest of the scientific community. See, the power of science comes here. See, I have made some kind of prediction and I have done some testing, and based on that, I might conclude something, right? I might actually conclude that the geocentric theory is true. But the power of science is anyone can retest my predictions. Anyone can say that if this geocentric theory was true, then such and such thing, they can make new predictions and then test those new predictions against this theory. So if this geocentric theory was true, then this and this would have also happened. See, that is where the geocentric theory actually failed, because it doesn't really explain how the seasons happen, for example. Right. So it might be able to explain how day and night happen, but it fails when someone else, not me necessarily, someone else actually came along and said that let me see whether the geocentric theory can actually explain the seasons, and then he or she would make more predictions, would actually collect more data to test their prediction, and then they would say that, oh, actually the geocentric theory does not really work. And now, of course, what they would do is that they would say that, okay, because the geocentric theory does not work in explaining something as basic as season, we could actually reject that theory. And they would come up with a new theory to explain their new observations. And that is where the power of the scientific process lies. We are always evolving as scientists, right? Everyone is a scientist. Anyone, each and everyone, from little child to very old people, right? All of us are scientists, because every day we are observing something. We are then saying that this is why such a thing might have happened, right? We are forming a hypothesis. Then we would see whether our hypothesis is really true or not. We'll collect some kind of data. We might actually gather opinions. We will do something to actually test whether our hypothesis is true. And then based on that, we would either accept that hypothesis, whether our original hypothesis is correct, if it turned out to be correct, or reject that hypothesis. So this process, whether either knowingly or unknowingly, we are following every day, even in making small conclusions. And this is the power of that scientific process. Now, there are several examples of why this scientific process actually was so powerful, right? So one of them, there are several aspects to this, and we would understand each of those aspects in a little bit detail, right? And the idea is that you don't have to learn all of those things. You just have to appreciate the painstaking detail in which the scientists actually work. And then that would give you an appreciation of how rigorous their science is, how rigorous their maths is, how rigorously they test their predictions against the actual data, how hard they work to keep the sanctity of this scientific process. So one of the first examples is that of Kepler and Brahe. See, Kepler was he was an observationist. So what actually it means that there are two kinds of scientists. One is those scientists which are involved in experimentation. The other kind of scientists are those which are involved in collecting the data. So data collection, right, those kind of things were actually done by Brahe. So Tycho Brahe was another scientist, and he collected extensive data on planetary motion. So planetary motion, until Kepler was there, was believed, we already knew that the sun was at the center. We already knew this much. Okay, so we had already gone to the heliocentric theory, and then we were saying that there were circular orbits in which the planets were revolving, right? So this was one of the planets, let's say Earth. It is revolving in circular orbits, and this is the key. What we were saying till then, when Kepler and Brahe came along, this was the standard idea. This was the accepted sort of theory of the planetary motion, that the orbits of the planets was circular around the sun. Brahe actually collected extensive data, okay, and this data was analyzed by Kepler, right? So Brahe collected the data, saying that, okay, let me see what the angle of the Earth and the angle of the sun is, and right. So there were two times he did the measurement. So this was the let's say Earth and Mars, two planets he took, and how much angle changes happen over a certain period of time. Okay, so this is the kind of data that Brahe had actually collected. Okay, so measuring from the sun, what was the change in angle of the planets over a certain period of time. So that was the data that Brahe collected. Kepler used the data. So Brahe was no longer working, and it was Kepler who actually used that data to tell us that no. The data that Brahe has collected actually refutes the theory of circular orbits. It tells us that the orbits are not circular but elliptical. Okay, so this is an elliptical orbit. It is slightly flattened and elongated on one side and flattened on other side. It's like a circle. We'll study it in detail in maths. And of course, sun is in the sort of center of this new elliptical orbit, and planets revolve around this. And this gave rise to the Kepler's three famous laws, and those of course we will again study a bit later. See, that is the key. One of the things that you have to understand is that the old model was given by Nicholas and Copernicus, and this model, Nicholas was the first name. So the Copernicus model of the circular orbits was rejected in favor of the Kepler's model, because not only by Kepler but by entire scientific community, because it explained the observations made by Brahe quite well. The observations of Brahe were not that different from what would have happened had there been circular orbits. So the calculations had to be precise, and those things were done by Kepler. Another example, another most important thing, see, that is what tells us that science is very, very collaborative. That was the first example, because Kepler and Brahe, so the collection of data, everything was done by Brahe. Kepler did more computation on that data and finally came up with this idea that based on the observations done by Brahe, Kepler actually said that was the collaboration. Kepler and Brahe, they worked together. Another important thing about science is that the theories done by the previous scientists are always improved upon by the subsequent scientists, subsequent physicists, and that's the most important aspect. Some of the observations, what is known till now, is explained by a particular theory. What I observe in the future, my power of observations are actually increased, right? So for example, telescope was not there in the beginning. Then telescope came. Now we have very powerful telescope. Now we have rockets, so we can go to space and observe more things, right? So all of this increases our observation power, right? Microscope was not there. Now we can even see, using electron microscope, we can even see the nucleus, right? We can go till there. So my powers of observations are actually increasing, and because of my power of observation is actually increasing, I am trying to use the existing laws to explain why I am seeing particular thing. But those existing laws were devised when such a observation power was not there. So those laws might actually fail, and then I would have to come up with a new theory to explain my new observations. And that is what has happened. For example, Newton's theory of gravitation was the beginning of systematic science. And Newton was not only a very prolific scientist, he was actually a very good mathematician. So that is what we have to understand, that some of the times you will see that lot of these scientists that we will talk about are also good philosophers. Philosophers means they continually think about knowledge. What does it even mean to know something, right? That's what philosophy is. So lot of these scientists are actually good philosophers, and they are some of these physicists are actually very good mathematicians as well. So that is what one thing that I want to touch upon. See, if you are good in physics, then you might naturally become good in mathematics as well. So there is a positive aspect of this. See, Newton's law of gravitation is very basic. We know that, right? So what does it tell us? It tells us that the force of gravitation is equal to G m1 m2 upon r square. If I remove this universal constant of gravitation, if I do away with this, then its equality will become a proportional sign, and okay, so the force is directly proportional to mass, product of the masses, and inversely proportional to the square of the distance. This is what this law is telling me. The problem with this Newton's law was that it actually failed when it actually worked only for very limited range of physical condition. So when does the Newton's law actually fail? The Newton's law actually fails when the things are observed at high speed. So the speed becomes very high, then Newton's law of gravitation does not really work. So that was the thing. Previously we were not even dealing with these high speeds. We were only looking at apples falling from trees, and Newton's law of gravitation is actually, Newton's theory of gravitation is actually sufficient to explain the observations that people were doing, the terrestrial observations that we sort of indulge with in our daily lives. So Newton's theory of gravitation was sufficient for that. But then what happened was, we were looking at the stars, we were looking at the light coming from the galaxy, we were looking at a lot of other things because our power of observation had increased. And at that point we realized that, oh, the Newton's law of gravitation does not really work if the speed of the things that we are concerned about is very close to the speed of light. Right? Not very close, but it is sort of a fraction of the speed of light. And at that time, of course, Albert Einstein came up with his famous theory of general relativity. So general relativity came along and explained those aspects where Newton's law of theory of gravitation did not really work. Okay, so it covered sort of more areas. So it doesn't mean that Newton's theory of gravitation is wrong. It just means that Einstein's theory of general relativity is more applicable than Newton's theory of gravitation. Of course, now we also know that even Einstein's general theory of relativity does not really work at places like center of the black holes. Now we are able to observe black holes. So of course we will try to apply our existing theories to the centers of these black holes, where the mass, both the mass at the center of the black hole and the speeds that we are encountering there are very high. And we know that the Einstein's theories actually fail in this case. So in that case, we are trying to come up with a new kind of sort of theories which are encompassed in the field of quantum mechanics. So this is a constant process of science. So science, we start with something, we try to explain whatever we have seen so far and we construct certain theories around it. Then some new observations come along and refute our theories, and then we construct even larger theories which encompass those observations as well. So improvements are, so if you create a theory and your theory is refuted, it does not mean that you have been unsuccessful. It just means that you are actually very successful and somebody took the trouble to refute your existing theories and give new theories. Now, another important thing about, of course, the dynamics of science is that it is able to, we always encounter unexplained observations, and that is the most important thing. There are always fringes of science and fringes of physics. There are always things that we cannot really explain, we cannot really predict. Okay, so that was the thing. For example, like we said before, Newton's laws of motion, they do not explain the motion of very small particles like atoms, electrons. They do not work there. And or things like where the particles are moving at very high speed. So again, Newton's law fail there. And of course, those were explained by the Einstein's theory, like we said. And the when the motion of particles is near light speed, those things are when the motion of particle is at light speed, those things are explained by the theories of relativity, Einstein theory of relativity. When the particles are very, very small, like electrons, protons, and even smaller particles than that, then those things are explained by quantum mechanics. The behavior of those things is explained by quantum mechanics. Another famous example is that previously we were dealing with the wave theory of light. So wave theory of light was the accepted theory of light. Then Einstein came along and he gave the new theory of light, which was the based to explain the photoelectric effect. So Einstein thought that there was this effect, photoelectric. What does it mean? It means that if light is shown upon certain materials, electrons are emitted from it. And to explain the observations that he took on this effect, Einstein really had to develop a new theory, the quantum mechanical theory of light. Another aspect of the dynamics of science is that we have a new theory, and based on that new theory, we come up to a new reality. So for example, scattering of the alpha particles. So scattering of this is a very famous experiment by Ernest Rutherford. What he did was that he took a gold foil and he bombarded it with alpha particles, and the alpha particles scattered. Now the scattering was not what was expected by the models of atom. So the atomic modeling was done. They thought that this is how atoms should be, but the scattering which Ernest Rutherford observed in his gold foil experiment, the scattering of alpha particles, was not in line with the accepted models of atom at that time. So Rutherford had to really create a new model, and based on the new model of Rutherford, further improvements were done by Niels Bohr. Right. So one of the things about this is that our reality actually changed based on these models. Right? Think about it. In those times, we didn't have powerful enough microscopes to be able to actually observe the atom. So all that we knew about the atom, the simplest building blocks of the universe, all that we knew about them actually came down to our modeling of it, what we thought it looked like. We really didn't know what it looked like. I mean, we were not able to observe it. So all we did was we thought this is how it must have been. I mean, in those times, if you were there, if I was there, then I could have thought, oh, maybe it looks like a basketball, maybe it looks like a cricket ball. Right? I mean, so all of those things were valid because no one had actually seen the atom. The only thing was that the models had to explain the observations. Right? So various experiments were done, and those observations had to be explained. The observations of those experiments had to be explained by the model. And so that's why there were so many models of the atom, because every time somebody would do an experiment, oh, this model, the older model of the atom does not really give us the predict the results that we have seen in this experiment. Oh, so let me come up with a new model. Okay, and that's why there are so many models of the atom itself. The model is something which we think is, but it might not be really this. Okay, so model is a concept that we use in our mind to understand how things must behave. That is not how things actually are. Okay. Now, another example of this, so with the model of atom, every time a model of atom changed, our reality actually changed. Right. So new theory of a new model of the atom changed the reality completely. As soon as the scientists got a new model, okay, this is the better model, they would again try to do something new with it. Okay, it gave rise to completely new sciences. Right. So for example, quantum mechanics, right, that was given a great thrust based on the Bohr's model. Before the Bohr's model, it was not very accepted, but after that, it really gained a lot of acceptance. Similarly, we again have the new theory. For example, Dirac gave the concept of antiparticle. So that was the new theory. It was just a theory. It was not the reality. Okay, he just thought that antiparticle might really exist. Okay, so we are creating a new theory. But later on, this theory which the Dirac actually created helped explain certain observations later on. So for example, the Carl and Anderson really observed an antiparticle of electron, and we call it positron. So positron is just like an electron, exactly like an electron, but instead of having a negative charge, it has a positive charge. Remember that positron is not a proton. Proton has a mass which is different from electron. Positron has the same mass as that of an electron, only the charge is different. So that was the thing. So there are several aspects to how physics actually works. Now let us look at what is physics, right? So we already saw there are several aspects of scientific process. There is collaboration, then there is theory, there is practical, right? All of those things are an endeavor to do what, right? That is what physics is. So physics endeavors to find the basic laws of nature. That is the main goal, okay? And those are the laws which govern the entire physical universe. And like I said, the ultimate goal of physics is to enumerate all the laws in such a way that we will be able to completely predict the future of this universe. And that is the ultimate goal. Of course, we might not get there, but slowly and gradually we are definitely going there. That is the journey. So that is the goal of physics. See, imagine that you have never seen a particular game, right? So for example, you are watching chess being played for the first time, or you are watching cricket being played for the first time. This is the first time you are watching it, so you don't know any of its rules. This is how the universe is. The universe is playing out in front of us, but we don't know any of its rules. So what would we do? To make sense of what is happening in the field, what would you do? You would really understand, you would see that, okay, when the ball actually hits the wicket, then the person who is in front of the wicket, the batsman, leaves. Okay, so that's the we know that that's the bowled. Okay, so the person got bowled, so he has to now leave. But suppose that if we didn't know that rule, just by watching the game, we can come up with that rule. And that is what the physicists, that is what the scientists are actually doing. They are watching the universe in front of them playing out and trying to come up with rules in that case. Rules which would explain what they are saying. Now, there are two basic principles in physics. One is unification or amalgamation, and the second is reductionism. So the first we will look at the unification. What does it actually mean to unify things? Unification is the most important endeavor of the physics. What it tells us is that I am trying to combine all the laws of the universe into as few statements, as few basic laws as possible. So for example, the apple falling from the tree happens due to gravitation. That's what Newton said. Also, the motion of the planets around the sun is governed by gravitation. It is the same basic law which governs both the motion, and that was really a big genius, right? Think about it. One is like giant bodies in the sky with not here on the earth at all, just somewhere in the universe, giant bodies, and they are observing, they are following the same basic law. The law of gravitation remains the same whether we are talking about those giant bodies or simply an apple falling down a tree. That's a big deal. So those kind of unifications take mankind, take the humankind, they just take us leaps and bounds beyond where we are today. So that was the thing, right? So that is the most important goal of physics, to unify all the working of this universe into as few laws as possible. The second important aspect of the physics or the science also, right, is actually reductionism. What does reductionism mean? It means that as soon as I see something complex, so for example, as soon as I see this remote control, what I'll try to do is that I'll try to reduce it to its basic parts. So I'll try to open it up. I'll try don't actually do this at your home or at your school, but this is what I would actually do. I would just try to tear it apart, break it into constituent parts. For example, here is a motor. This is a simple motor, okay, very simple motor. I have just broken it into its constituent parts. So I came up with a battery. Now, if I open this remote, again I will come up with a battery, right? Notice that these components are the same. So what I am trying to do in reductionism is trying to break the complex system into simpler parts and understand the working of each simple part. Once I understand the working of that simple part, for example, I understand the battery, how does the battery work in the case of a motor, how does it work, I can then understand, use the same battery to power my remote control, right? So once I understand how do constituent pieces work, it gives me two advantages. First, I can use those constituent pieces to somewhere else, and second, by understanding how the constituents work, I can then understand how the whole thing works all together. So those are the two basic goals in physics. With this, we end this lecture. Of course, we will continue further with the lecture, but this is what I want you to think. I want you to think about why physics, why science is so important in our life. And once you appreciate it, you will really develop interest in science. Don't just study it for getting marks. You will study it to understand the world around us. And hopefully that would also help you fetch good marks, also help you do the numericals very, very quickly. Thank you.